Welcome back to Sophia's chemistry class. Today we're talking about energy change. So chemical reactions, which we're going to start calling systems going forward, all share one thing in common. They all have the capacity to do work and transfer heat, known as energy. And since, according to the first law of thermodynamics, energy can't be created or destroyed, the energy is transferred between a system, or the chemical reaction, and its surroundings. Everything that surrounds the system, basically the universe. And a system where neither energy nor matter are lost, which is realistically an impossible feat, is something we like to refer to as an isolated system. And we use isolated systems, or our imitation of isolated systems, to measure the total energy that is gained or lost within a system, also known as enthalpy change. Because enthalpy is the total amount of energy within a system, and it's impossible for us to know it, but we're only able to determine how much is lost and how much is gained in the form of usually heat. And the process of determining that change in enthalpy is known as calorimetry, which uses a calorimeter, which is an apparatus to conserve as much energy as possible. All chemical reactions or interactions between a system and its surroundings both take and require energy to start and both produce energy. However, depending on the quantities that they require and produce, they can either be endothermic or exothermic. Endothermic reactions require a lot of energy to begin, and they don't produce that much energy once the reaction is over, meaning they gain more energy than what they take out. So overall, they're gaining energy, which we'll use Q because they're gaining heat. Whereas exothermic reactions require less energy than they actually produce, meaning overall they're losing heat and they're losing energy. A simple way you can remember this is by associating endo with the word in and exo with the word out. To calculate the change in enthalpy in a reaction, the equation Q equals mCT is used, where Q is the heat or the change in enthalpy in the system. And remember, it can be negative or positive depending on whether or not the reaction is endo or exothermic. M is the mass of the substance in question. C is the heat capacity of it. Now, heat capacity is essentially how much energy in joules is required to raise the temperature of a specific substance by 1 degree Celsius. Since heat capacity is unique for every single element or every single substance in question, it is only able to be determined empirically. So usually when you're doing a question, the heat capacity will be provided to you. And delta T is just the change in temperature, because temperature is essentially the energy that is stored within the bonds of a substance. So if the total energy, the enthalpy changes within a system, then the temperature is also going to change. So let's do a practice question. A very simple one. When 600 milliliters of water in an electric kettle is heated from 20 degrees Celsius to 85 degrees Celsius, how much heat flows into the water? So we're solving for Q, and our M is 600 milliliters of water, but we'll have to convert that from milliliters into grams. Since the density of water is 1 gram per milliliter, the mass of the water in grams is also just going to be 600 grams, since the milliliters cancel out. Then we're looking for the heat capacity of water. The heat capacity of water, I'll just tell you right now since you'll probably have to search it out, is 4.18 grams per joules times degrees Celsius. Joules times grams per degrees Celsius. Next, the change in temperature. The initial temperature of the water was 20 degrees Celsius, and the final temperature of the water was 85 degrees Celsius. This means that the water increased by 85 minus 20, so 65 degrees Celsius. So we add that to our calculation as our change in temperature. So all we have to do really is just plug this into our calculators. 600 times 4.18 times 65. And we get 163,020 joules. And since that's such a huge number, we might as well just convert it into kilojoules, which would be 163 since we're rounding. When it comes to representing whether or not the enthalpy has changed in the reaction, there are 4 methods that we could use. We use this just to show that the energy is not the same amount as it was before, and to show exactly how much energy it produces or consumes. So the first way we do it is by including the enthalpy change as either a product or reactant. So, for example, we'll take water plus sulfuric acid plus 200 kilojoules turns into H3O plus HSO4. Here, the energy has been represented as one of the reactants. And it shows you that, yes, energy has been added to the system in order for the reaction to take place. The same thing could be done with an opposite reaction where energy was produced in an endothermic, where we would just move the amount of energy to the other side of the arrow. And the next way we could illustrate this reaction is by, rather than including the energy as one of the products, we write on the side that this much energy had been removed or this much energy had been produced. So for example, we'll do the exact same equation. I did not include states just for the sake of time. And then we would write the change in enthalpy was 200 kilojoules. And notice I'm putting it as a positive because this is an endothermic reaction. This reaction was gaining energy. If it was exothermic and the 200 kilojoules was on the right side with the products, I would write negative 200 kilojoules. The next way that we would illustrate an enthalpy change would be with molar enthalpy. So here we know that the total amount of energy change was an increase of 200 kilojoules. But what if we didn't know that and we only knew how much it increased by per mole of the reactant? In that case, we would put Hx, depending on the type of reaction, per mole, making it pretty straightforward. And the final way that we represent an enthalpy change is with diagrams. And this is probably the easiest one. So, in the case of the diagrams, our y-axis is going to be the energy, and our x-axis is going to be the progress of the reaction. So, in an exothermic reaction, if we were to start off with this much energy, and we would end up with this much energy, because when the reaction took place, this much entered the bonds, entered the surroundings of the reaction, the total energy, the total enthalpy change had decreased. So we would see that energy had been removed from the system. The collision theory states that reactions occur when particles collide with each other in the correct position with the correct amount of energy. Once the necessary amount of energy is present within the system, aka the activation energy, the reactants will consume that energy to reach an unstable transition state. Since the transition state isn't stable and viable for the compound, it will have to release some of that energy that is stored within its bonds and transition into the products. If the energy consumed is more than the energy released, the reaction is endothermic, and if the energy consumed is less than the energy released, then the reaction is exothermic. An increase in the amount of energy or in the amount of particles that are correctly positioned can increase the speed at which the reaction occurs, as collisions between particles become more effective. And when the rate of reaction is constant, particles with the correct orientation and the amount of activation energy are inversely proportional, meaning that as the amount of particles with the correct orientation increases, the activation energy becomes lower. And because less energy is required to push the particles into the correct places. There are different factors, including concentration, temperature, surface area, and the presence of a catalyst, and the nature of the reactants in a reaction that can increase the number of effective collisions and increase the rate at which a reaction takes place. In the case of concentration, when there are more molecules present as a whole, there's a higher chance for them to collide with each other in an effective way, meaning the amount of collisions that actually work will increase, so there's going to be more effective collisions. And in the case of surface area, when there is a larger surface area of a molecule, there's more potential places where different molecules can collide with each other to incite a reaction. So just like with concentration, there's a higher chance that the collision that occurs is going to be effective. And in the case of where a catalyst is present, the catalyst is going to physically move the particles together, the molecules together, so that when they do react with each other, it's going to be a lot more effective. When it comes to the nature of the reactants, some reactants, like noble gases, simply are just not prone to engaging in reactions, so the reaction rate will be decreased exponentially because they just won't cause a reaction to take place. And in terms of temperature means that the reactants are a lot more energetic, so they're more likely to bump into each other in an effective way. And they're more likely to bump into each other in general, meaning that they're going to have a higher chance of having an effective collision.